Hi, I'm Jeff Groh. Welcome back to Calculus 2. Today, we're going to talk about Taylor polynomials. Suppose you have some function. We already know the tangent line approximation. The tangent line approximation uses the coordinates of a point and the slope. The equation of the tangent line, which you can derive easily enough yourself, is f prime of x is f of x naught plus f prime of x naught times x minus x naught, derived using the point slope form of the line. What characterizes the tangent line? If we think of the tangent line as being a function, note that if we evaluate this equation for a straight line at x naught, x minus x naught is 0, and so you get f of x naught. The line has the same height as the function at the point x naught. Also, the derivative of this function g, the derivative of x being 1, will be the constant f prime at x naught, which means that g prime at x naught equals f prime at x naught. We could say that the tangent line is the unique polynomial of degree 1 that has the same function value and the same slope as the function f, clearly seen by the picture that we drew earlier. The same height and the same slope as the function f at a particular point x naught. But what's to stop us there? Why not seek a function g such that g has the same function value at x naught, the same slope as f at x naught, and the same concavity at x naught? It would require, in this case, since straight lines have second derivatives equal to 0, it would require that we have at least a quadratic polynomial in this case. Suppose our function g has the following form. It's going to be some constant, another constant times x minus x naught, and another constant times x minus x naught squared. If g of x naught equals f of x naught, when I plug in x naught here, I get 0 and 0 in the last term. We know that g of x naught is a naught, which tells us what that constant has to be. A naught must be the function value of f at x naught if g and f are to match function values. What about slopes? G prime of x, in this case, is going to be a1 plus 2 times a2 times x minus x naught. To match slopes with f at x naught, what has to happen? Again, we're substituting x equals x naught into the formula for g prime, and we get a1. So the constant a1 must be the slope. So far, we know this constant a naught must be f of x naught, and the constant a1 must be f prime at x naught. We seek a polynomial that matches the concavity. So calculating the second order derivative, we get twice a2. That means that if we evaluate the second derivative at a0, we don't get a2, we get twice a2. And we demand that that be the same as the second order derivative of f at x0. It follows then that a2 is 1/2 f double prime at x0. It follows that if we seek a quadratic function that matches the function value of a given function f, the slope, and the concavity at a single point x0, then that polynomial is given by f of x0 plus f prime of x0 times the quantity x minus x0 plus 1/2 f double prime at x0 times x minus x0 quantity squared. More generally, suppose we seek a polynomial of degree n. Let's rewrite this polynomial as the sum, as k goes from 0 to n, of a sub k x minus x0 to the power k. This would be a0 plus a1 times x minus x0 plus a2 times x minus x0 squared plus ... plus a sub n x minus x0 to the power n. Suppose that we require that this polynomial equal a function at x0, it equal the slope of the function f at x0 all the way down to the nth order derivative. This is going to match not only the function value, the height, the slope, the concavity, but all the way down to the nth order derivative is going to match this function, but only at that one point. What are the constants a0, a1, a2, and so on? As we've already seen, the function value f of x0 will equal a0. That's because all of these terms involving a1, a2, and so on will be multiplied by 0. So that f prime of x0 is equal to the slope of this polynomial at x0. We require a1 be f prime at x0. When we evaluated x0, these terms after a1 go to 0. This is working out just as before for the straight line that matched function value and slope, and for the quadratic that matched function value, slope, and concavity. Pretty easy to see that on the next derivative we're going to get twice a2 equal to f double prime at x0. As a bit of a theorem, I claim that the kth coefficient is in fact the kth derivative at x0 divided by not k but k factorial. We're going to make a definition. The nth degree Taylor polynomial of f centered at x0. First of all, it's denoted by Pn of x. The nth degree Taylor polynomial centered at x0 is the sum, as k goes from 0 to n, the kth derivative evaluated at x naught times x minus x naught to the power k over k factorial. That's equal to f of x naught plus f prime of x naught times x minus x naught plus f double prime at x naught over 2 factorial x minus x naught squared plus the third order derivative at x naught divided by 3 factorial times x minus x naught cubed until you get to the nth order derivative evaluated at x naught divided by n factorial x minus x naught to the power n. These are nth degree Taylor polynomials. Believe it or not, Taylor polynomials centered at the origin at x naught equals 0 have a different name. They're called Maclaurin polynomials. In these, we just set x naught equal to 0, so that the Maclaurin polynomial will be summed from 0 to n. You'll have the kth order derivative evaluated 0 divided by k factorial times x to the power n. So these look like f of 0, f prime of 0 times x, f double prime at 0 divided by 2 times x squared, up to the nth order derivative at 0 divided by n factorial times x to the power n. Maclaurin polynomials are Taylor polynomials just centered at 0. That's all. Why do we need a different name? Well, it turns out Maclaurin was a more influential mathematician than Taylor, though Taylor's formula was slightly more general in this instance. Maclaurin truly was an impressive individual, earning his doctorate by the age of 16. I want to do some examples. Let's try f of x equals sine of x, and let's find some of the Maclaurin polynomials associated with sine of x. To do this, we're going to make, first of all, a list of derivatives. The next derivative, the fourth derivative, is back to sine of x. So this will repeat every 4. We'll evaluate these at 0 since we're finding Maclaurin polynomials. If I evaluate sine at 0, I get 0. Cosine evaluated at 0 is 1. And these numbers will also repeat. It follows then P0 of x is 0. P1 of x is 0 plus 1 times x minus 0, or x. P2 of x is 0 plus 1 times x plus 0 times x squared. In other words, the second degree Maclaurin polynomial is the same as the first degree Maclaurin polynomial for the sine function. For the third degree Maclaurin polynomial, we'll have minus 1 divided by 3 factorial x cubed. Continuing in this pattern, P4 of x is going to be P3. P5 of x is going to be x minus x cubed over 3 factorial plus x to the 5 over 5 factorial. One thing you should notice about the Maclaurin polynomials for the sine function is that they only have odd powers of x. Remember, sine is a function that is odd. Do you remember what the definition of an odd function is? That means sine of negative x equals negative sine of x. Negatives pull out. Odd powers of negative values produce a minus sign, which could be factored out. If any of these terms had even exponents, negative would be squared away and would not be able to be factored out. I want to plot the graph of these Taylor polynomials. Let's define n to be 1 for a moment. I'm going to define my polynomials to be functions that map x into the sum. The sums are going to be of the form -1 to the k, to the power k, times x to the power of 2 times k, 2 times k plus 1. And we're going to divide by 2 times k plus 1 factorial. K goes from 0 to the value of n that we've chosen. And I want to plot these functions against the sine function. We'll go from minus pi over 2 to pi over 2 on these. Oops. I want both curves to be black. You'll be able to see which one is which based on the graph. Oops. Doesn't like my parenthesis there. Let's see here. If n is equal to 0, 2 times 0 plus 1 is 1. We'll have the Taylor polynomial of degree 1. And we get this straight line right here. Let me add one more command in here. Scaling equals constrained. That means you have the same scaling on the x-axis as on the y-axis. 1 inch here will be 1 inch here. So you can see which is which. If I make one red, perhaps it's clearer. You can see that the Taylor polynomial of degree 1, the Maclaurin polynomial of degree 1, is the tangent line approximation, and both the curve and the tangent line go through the origin at a 45-degree angle. If I make n equals 1, 2 times 1 plus 1 is 3. That'll be the polynomial of degree 3, and you can see that the cubic now matches a little bit better. Let's have this go all the way out to minus pi to pi, so it's a little bit farther out. You can see that the red now is the cubic, and the black is the sine function, which oscillates back down to the axis here. This is how well the cubic polynomial matches. What about 5th degree? 2 times 2 plus 1 is 5. This will be the Maclaurin polynomial of degree 5. You can see that the match is a little bit better. We'll make this a little bit bigger so you can see it perhaps a little better. And that's the Maclaurin polynomial of degree 5 here. If we go out even a little bit further on each side, it makes it very clear which is which. With scaling equals constrained now, I better change my view. We'll make this go from -5 to 5, -5 to 5, and I need to put a little comma there. It's pretty clear which is the sine function and which is the Maclaurin polynomial of degree 5. 1 bump, 2 bumps, 3 bumps, 4 bumps, n-1 bumps. The match is pretty good. That was with n equals 2 up here. What happens if we make that n equals 3? The match goes even a little bit further out. If I make this 4, 2 times 4 is 8 plus 1 is 9. That's the Maclaurin polynomial of degree 9. It's now going a little bit closer, a little bit farther out. 5. The match is really close in here now. All the way out to about negative pi to pi, or negative 4 to 4 now, it looks like. What if we make this 6? That's the Maclaurin polynomial of degree 13. 2 times 6 is 12 plus 1 is 13. The match is way out here now. Very close. 7. The match is all the way out here almost to -6 to +6 now. The curves are lying almost on top of each other. The higher we make that degree, the better that match is on a larger and larger interval around the point where we get the function values to exactly match, and that is at 0 in this case, since we centered this at 0. What if we go a little bit further out with this same polynomial? -20 to 20. One thing you'll see here is that the match was very good until a certain point, and then it got really, really bad. It looks pretty clunky here, and that's just a function of not plotting very many points. I can make the function, I can make my computer plot more points, and you can see that the curve is smoother now, but it still is very, very bad. After all, with n equals 7, we're dealing with a polynomial of degree 15. When you raise numbers like, say, 10 to the power of 15, 10 to the 15 is an enormous number. This is going to go really, really crazy out on the endpoints, and that's perfectly characteristic of Taylor polynomials. They'll match very, very well on some finite domain, but once you're off of that finite domain, the match is very, very poor. Polynomials, after all, of high degree have a lot of wiggle, and they blow up pretty rapidly. What if I make this n equals 10? The match goes a little bit further out. If I make it 20, even farther out. If I make this 40, now the match is good between -20 and 20, and I don't see any difference. I'll have to back out a little further to be able to try to see any of the differences here. No difference from -30 to 30. How about -40 to 40? Yep, we finally have that difference just after -30 and 30 on the endpoints. So I think you can see these Taylor polynomials, and in this case a Maclaurin polynomial, they match the function exceedingly well on some finite interval. That interval tends to get bigger and bigger as the Taylor polynomial degree gets higher and higher, but so does the deviation once you're outside of that interval. That deviation gets worse and worse because you're dealing with a very high degree polynomial. When n equals 40 in this case, 2 times 40 is 80 plus 1. We're dealing with a polynomial of degree 81. 10 to the power of 81 is an absolutely enormous number. Let's derive Maclaurin polynomial approximations to other functions that you know and love. The simplest one is e to the x, because all of its derivatives are e to the x. And so if we evaluate those derivatives at 0, we get 1. Remember that the nth order Maclaurin polynomial was the sum as k goes from 0 to n of the kth derivative evaluated at 0, which will be 1, divided by k factorial, x minus 0 in this case because we're dealing with a Maclaurin polynomial, to the power k. We see then that the nth order Taylor polynomial is going to be, when k is equal to 0, x to the 0 is 1, 0 factorial is 1. We'll have 1. When k is 1, we'll have x. K is 2, x squared over 2 factorial. X cubed over 3 factorial. And we'll stop at x to the n over n factorial. Note that this has both odd and even powers of x, and e to the x is neither even nor odd. It's kind of a mix of both. Every function can be decomposed into an even part and an odd part. Given a function f, there exist functions g and h such that f of x is g of x plus h of x, g is even, and h is odd. So every function can be decomposed into a part that is even and another part that is odd. At least these functions that are defined on are, I'm assuming here, that the domain of f is, let's say, the entire real line, or at least some interval that is symmetric about the origin. We can prove this easily enough. We'll construct the function g and the function h. G is going to be the even part. Suppose that part is f of x plus f of minus x divided by 2, and h of x, the odd part, is f of x minus f minus x over 2. You can see that because we're evaluating at minus x, that the function has to be defined on an interval that is symmetric about the origin. It's easy to know that if you add these two, the second terms in each part will cancel out. We'll have f of x over 2 plus f of x over 2. That adds up to f of x. So every function f can be decomposed in this way. It only remains to prove that g is even and h is odd. So we'll appeal to the definition. A function is even if, when you replace x by negative x, it stays the same. In this case, you get f of minus x plus f of minus x. Because addition is commutative, I can reverse the order, and the minus and negative cancels. We end up with f of x plus f of minus x over 2, and that is g of x. Therefore, g is even. Similarly, h of minus x will be f of minus x minus f of minus x over 2. Minus minus will cancel. When you reverse the order of a subtraction, you generate a minus sign. And we have minus h of x, so that h is odd. Returning to our Maclaurin polynomials for e to the x, you see that we can decompose this into an even part. This will stop someplace. And the second term is odd and also terminates someplace. Depending upon whether n is even or odd, that term will be here or here. What about the Maclaurin polynomials for sine x? In that case, we had x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, and so on. Notice that we have only odd powers here. In this case, the even part, h of x, would be identically 0. What about cosine of x? As you know, cosine is an even function. Let's list its derivatives. The fourth derivative will be the same as the 0th. It will repeat after this. Evaluating at 0, all of the odd derivatives are 0 at x equals 0. Follows then that our nth order Maclaurin polynomials are going to be 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus, and it'll terminate someplace at the appropriate value of n. I want to go back and look at, for my function e to the x, the polynomials that we had were x to the power k divided by k factorial. Let's see how well we're doing approximating the function e to the x, which is shown in red here. If n is equal to 2, we're dealing with a quadratic approximation, which matches the slope at 0 and the concavity, but you can see that it's still just a parabola. If we make that degree 3 instead, now we have a cubic approximation to the function e to the x. If we make this, say, 5, degree 5, or degree 8, the degree 8 approximation is really good for a little while, but of course polynomials blow up. As you move out to the side, this exponential function decays to 0. Though the match is incredibly good on this little finite interval. The match will be quite poor as you go farther and farther out. If we make n equals 10, n equals 100, well, now the curves are one right on top of the other, and you can't tell the difference. Unless you go farther out, like say negative 50 to 50, you'll definitely be able to tell. Notice all the wiggling going on out here. We're dealing with a polynomial of degree 100. Polynomials can oscillate a large number of times, n minus 1 times.
A quadratic has 1 bump. A cubic can have up to 2 bumps. A quartic up to 3 bumps. A polynomial of degree 100 can have up to 99 bumps, so it can have 99 turning points. And as you can see, we're getting that kind of oscillation here out at the end. Nonetheless, the approximation is really quite good, at least on some finite interval. What about the function cosine of x? On that function, we only dealt with even powers because the cosine function is even, but it also alternates in sign. Oops, here I've done too much. Let's do n equals 2, and let's go from -5 to 5 again on our graph. Let's see, n equals 1 there. With n equals 1, 2 times 1 is 2, we're dealing with the quadratic approximation. And you can see that we're getting this quadratic to fit very nicely and snugly about x equals 0, y equals 1. If n is equal to 2, we're dealing with 2 times 2 is 4. That's a polynomial of degree 4. The match is pretty good, but again, 4th degree polynomials can have up to 3 turning points, and you can see those clearly here, not quite matching the turning points on the cosine function itself. But it's the best you can do in fitting a 4th degree polynomial onto the cosine function at x equals 0. What about 6? Now it's moving a little bit farther out. You can see that if we pull out here on an interval from -10 to 10, you can see that we're getting a 12 degree polynomial fitting pretty nicely to the cosine curve to a certain point and then pulling away later. You should ask yourself, how do calculators calculate the values of the trig functions between, say, 0 and pi over 2? You can use polynomials, and what is the advantage of using a polynomial to evaluate these trig functions? The advantage of a polynomial is you have only a finite number of additions, subtractions, multiplications, and divisions to perform. And using a high enough degree polynomial, you can make the function as accurate as you'd like between 0 and pi over 2, and then you can extrapolate from that interval on all of the other intervals. If n is equal to 10, that's a 20 degree polynomial. You can see the interval where we get a really good approximation is even wider. The higher that degree, the farther out. If I make it 11, it changes only a little bit because we're dealing with a 22 degree polynomial approximation now.
As an example, let's find P4 of x, the 4th degree Taylor polynomial approximation for the function ln of x centered at not equals 1. Use the approximation to estimate ln of 1.1. We begin by writing out f and its derivatives up to the 4th. The first derivative is, of course, 1 over x, or x to the minus 1. The second derivative is negative x to the minus 2. The third derivative is 2x to the minus 3. And the fourth derivative is minus, I'll write it as 3 factorial x to the minus 4. We'll evaluate all of these at 1. The natural log of 1 is 0. The first derivative at 1 is 1. The second derivative at 1 is negative 1. The third derivative evaluated at 1 is 2. And the fourth derivative evaluated at 1 is negative 3 factorial. It follows then that P4 of x is going to be 0 plus 1 times x minus 1 minus 1 over 2 factorial x minus 1 squared plus 2 over 3 factorial x minus 1 cubed minus 3 factorial over 4 factorial x minus 1 to the fourth power. Simplifying this, P4 of x will be x minus 1 minus x minus 1 squared over 2. This cancels, plus x minus 1 cubed over 3 minus x minus 1 to the fourth over 4. Evaluating at 1.1 gives us approximately the value of the original function, the natural log, at 1.1. You can see that we will have 0.1 minus 0.1 squared over 2 plus 0.1 cubed over 3 minus 0.1 to the fourth over 4, substituting x equals 1.1. 1.1 minus 1 is 0.1. So, how big is that? My calculator gives me 0.0953083333 and so on, whereas the natural log of 1.1 is about 0.0953101798. You can see we're good to the fourth decimal place. This example raises the issue of accuracy. How accurate are these approximations? You can see that you kind of would expect something close to a fourth decimal place accuracy because we're dealing with 0.1 to the power of 4 here. There must be a theorem that tells us how good these approximations are. And of course, there is, or else I wouldn't have brought it up. The theorem is called Taylor's theorem, and it has the Taylor remainder formula. The theorem goes like this. If f has n plus 1 derivatives, on an interval I containing x naught on an open interval I containing x naught, then for each x, an element of I, there exists some point between x naught, x, such that the original function is equal to the Taylor polynomial plus an error. Now, the question is, what is the form of this error, the remainder term? The remainder term is the n plus first derivative evaluated at the point z divided by n plus 1 factorial x minus x naught to the power n plus 1. It's the very next term in the Taylor polynomials for degree n plus 1, except instead of evaluating the n plus first derivative at x naught, you're evaluating it at some point z between x and x naught. That's how you get equality here. This gives you the exact error in approximating the function by the Taylor polynomial of degree n. This is a formula you're going to need to remember. Let's use the remainder formula to calculate the error in approximating some function that we know. So we're going to estimate the error in using P3 of x not equal to 0, to approximate f of 0.1, where f of x is the sine function. In this case, we already know what the third order Taylor, in this case, since the center is 0, the third order Maclaurin polynomial is. It's x minus x cubed over 3 factorial. The question is, how much error do you get in approximating the value of the sine function using this polynomial evaluated at x equals 0.1? The approximation itself is not a problem. You get 0.1 minus 0.1 cubed over 3 factorial. My calculator tells me this is 0.0998 and then a sequence of 3's. If I put my calculator into radian mode, I can calculate the sine of 0.1. My calculator tells me it's 0.099833416, so we're good to here. That's pretty good accuracy when you think about it. What does the remainder formula tell us about the nature of this error? The remainder formula tells us that we have to deal with the fourth derivative at some point z divided by 4 factorial x minus x naught to the power 4. What is the fourth derivative of the sine function? If you sit down and calculate it, you'll find out that the fourth derivative of the sine function is sine of x. So in this case, we're dealing with the sine at some place z divided by 4 factorial. X naught is 0 in this case, and x is 0.1. Four factorial is 24. But what about this z? Z is only known to be between 0 and 0.1. The thing about Taylor's theorem is it doesn't tell you where that z is exactly. In fact, it's a total mystery. It just guarantees the existence of that point. What we need to look at is the sine function, the fourth order derivative sine, between 0 and 0.1 is no more than the value of the sine function there. Sine is increasing on that interval. So to get the largest estimate for this, since we don't know exactly where z is, it's somewhere in here but we don't know where, we'll choose the largest value and declare that the error, whatever it is is smaller than that. We don't know exactly what the value of the z is, so we don't know exactly what the error is, but we can say it's no more than the sign at 0.1 over 4 factorial 0.1 to the power 4. How big is that? My calculator tells me that we have 4.2 times 10 to the negative 7. We're off by at most a 4 in the 7th decimal place. 1, 2, 3, 4, 5, 6, 7. We're off by only a 1 because over here we had 3, 3, 3, so on. We're off by a 1 in the 7th decimal place. The remainder formula gave us an upper bound on that error because we didn't know the exact location of this point z, only that z was somewhere between 0 and 0.1. So the best that we could do was to estimate this by the maximum value, which occurs at 0.1, since the function sign is increasing between 0 and 0.1. We can turn this last problem around. Find the degree n so that Pn of 0.1 approximates the sign of 0.1 to 8 decimal places. In this case, our tolerance for error is 5 times 10 to the negative 9. We can be off by less than a 5 in the 9th decimal place in order to have the correct value in the 8th decimal place. We require then that the remainder be to within this tolerance for error. This gives us 5 times 10 to the negative 9 is greater than whatever that n plus first derivative at z is, divided by n plus 1 factorial times 0.1 minus 0 to the power n plus 1. The function here, f of x, is the sine function. The thing about that is we don't know the value of n, so we don't know if we have plus or minus sine or plus or minus cosine. We want this to be an absolute value, and so we want either sine or cosine of z, whatever that z is, times 0.1 to the n plus 1 divided by n plus 1 factorial to be smaller than 5 times 10 to the negative 9. The thing about this cosine function is between 0 and 0.1, the function has values that are pretty close to 1. Since we're dealing with this in absolute value, just to be safe, we'll use the biggest this can be, which is 1, times 0.1 to the n plus 1 over n plus 1 factorial, and we'll have that less than our tolerance for error. To find the value of n that will work, all we have to do is plug different values of n in until we get a value smaller than 5 times 10 to the negative 9. We're really stuck just trying to plug numbers into our calculator until we find the smallest value of n where all of this works. I'm going to start by looking at n equals, say, 4. With n equals 4, I get the left-hand side 8.3 times 10 to the negative 8, which didn't quite do it. Let's try n equals 5. 5 plus 1 is 6, remember. Here I'm getting 1.388 and so on times 10 to the negative 9. As you can see, we can use these Taylor polynomials to approximate differentiable functions, functions with high levels of derivative on an interval, to whatever accuracy that we need.